This is GARIS Essays, that is 2-3 page opinion pieces on topics such as species dominance, the global state, politics, Femtotech, religion, society and education. Written by and read aloud by Prof. Dr. Hugo de GARIS. This is essay number 35, entitled Femtotech, Computing at the Femtometer Scale Using Quarks and Gluons, by Prof. Dr. Hugo de GARIS. Email profhugodegaris@yahoo.com. Website profhugodegaris.wordpress.com. Abstract. This essay shows how the properties of quarks and gluons can be used, in principle, to perform computation at the femtometer, that is 10 to the minus 15 of a meter scale. 1. Introduction. I've been thinking on and off for 2 decades about the possibility of a femtotech. Now that nanotech is well established and well funded, I feel that the time is right to start thinking about the possibility of a femtotech. You may ask, what about picotech, that is technology at the picometer, 10 to the minus 12 of a meter scale? The simple answer to this question is that nature provides nothing at the picometer scale. An atom is about 10 to the minus 10 meters in size. The next smallest thing in nature is the nucleus, which is about 100,000 times smaller, that is of 10 to the minus 15 meter in size. That is a femtometer, or a Fermi. A nucleus is composed of protons and neutrons, that is nucleons, which we now know are composed of 3 quarks, which are bound or glued together by massless photon-like particles called gluons. Hence, if one wanted to start thinking about a possible femtotech, one would probably need to start looking at how quarks and gluons behave and see if these behaviors might be manipulated in such a way as to create a technology, that is computation, and engineering, that is building stuff. In this essay, I concentrate on the computation side, since my background is in computer science. Before I started arcing, that's arcing, after retirement careering, I was a computer science professor who gave himself zero chance of getting a grant from conservative NSF, National Science Foundation, or military funders in the US to speculate on the possibilities of a femtotech. But now I'm no longer a wager, meaning working for a wage, salary. I'm free to do what I like and can join the billion-strong army of arcers to pursue my own passions. So I started studying QCD, quantum chromodynamics, which is the mathematical physics theory of the strong force, or it is known in more modern terms, the color force, color as in red, blue, green. Since I have a computer science background, I knew what to look for when sniffing through QCD textbooks to be able to map computer science concepts to QCD phenomena. 2. Bits and logic gates, the heart of computation. If you want to compute at the femto level, how do you do that? What would you need? To me, the essential ingredients of digital computing are bits and logic gates. A bit is a 2-state system. For example, voltage or no voltage, a closed or open switch, etc., that can be switched from one state to another. It's usual to represent one of these states as 1 and the other as 0. That is, as binary digits, binary B's and digits ITS, so B and the ITS, bits. It's an acronym. No, it's not an acronym. It's a short form for binary digits. A logic gate is a device that can take bits as input and use their states, that is, their 0 or 1 values, to calculate its output. The 3 most famous gates are the NOT gate, the OR gate, and the AND gate. The NOT gate switches a 1 to a 0, and a 0 to a 1. An OR gate outputs a 1 if one or more of its 2 inputs is a 1, else outputs a 0. An AND gate outputs a 1 only if the first and second inputs are both 1, else outputs are 0. There's a famous theorem in theoretical computer science that says that the set of 3 logic gates, not, or, and, are computationally universal. That is, using them, you can build any Boolean logic gate to detect any Boolean expression. For example, not x and y, in brackets, or, in brackets, w and z. So, if I can find a one-to-one mapping between these 3 logic gates and phenomena in QCD, I can compute anything in QCD. I would have a femtometer scale computation. That was the big prize I was after. So, I set out to find phenomena in QCD that I could map bits and logic gates to. I was quickly rewarded. It was a case of low-hanging fruit. I just happened to be the first person, as far as I know, wandering around the QCD orchard with a very specific type of cherry picking in mind. 3. The color charge on the quarks and the gluons. There are 4 types of force in the physical world. From weakest to strongest, they are the gravitational force, the weak nuclear force, the electromagnetic force, and the strong nuclear force. Actually, their relative strengths depend on the temperature at which these forces act. At extreme temperatures, energies, which occurred just after the Big Bang, and now at the LHC, Large Hadron Collider, in Geneva, their strengths converge to the same value, a phenomenon called grand unification. In the 60s and 70s, physicists became aware that the nucleons, the protons and the neutrons, consisted of 3 quarks, which have fractional electric charges, for example, plus or minus a third or 2/3 of the charge of an electron, and a new type of charge called color. The electronic charge came in 2 types, positive and negative, which is something science has known about for several centuries. The color charge, however, comes in 3 types, called red, blue, and green. Now, they're just labels, right? You could call them black, grey, and white, or alpha, beta, gamma, or whatever. The electromagnetic force is mediated, that is conveyed, between 2 electrical charges via the photon, the particle of light. A photon is emitted by one of the charges and is absorbed by the other. This interaction creates the attractive or repulsive force between the electrical charges. Something similar happens between quarks. The equivalent of the photon is called a gluon. A quark emits a gluon, which is then absorbed by another quark, and this creates the interaction between the 2 quarks. There's an essential difference between a photon and a gluon. The photon has no charge of its own, whereas a gluon does have a color charge. In fact, each gluon has 2 such charges. It is bi-charged, or bi-colored. This means that gluons can interact with other gluons, forming complex glue balls. I will not be using glue balls in this essay, but they might play an important role in Femtotech in the future! ! Strictly speaking, there are more than 3 color charges. In fact, there are 6, namely red, blue, green, and anti-red, anti-blue, and anti-green. A gluon, at least the type of gluon that I will use in this essay, has one of the first 3 and one of the second 3. So there are 6 such bi-colored gluons: a red anti-blue, a red anti-green, a blue anti-red, a blue anti-green, a green anti-red, a green anti-blue. In this essay, I will use only the red anti-blue and the blue anti-red gluons, because, using Occam's razor, they are all that I need. 4. Colors are conserved in quark-gluon reactions. How does a gluon interact with a quark? What happens? Remarkably, when a gluon and a quark interact, the gluon may change the quark's color, and in such a way that the colors are conserved. For example, imagine a red anti-blue gluon, which from now on will be abbreviated to GR anti-B. So capital G for gluon, which has 2 colors, R for red and anti-blue, or I'll just say not B, which means anti-blue. So GR not B, okay? Interacts with the blue-colored quark, abbreviated from now on to be QB. so blue-coloured quark. Quark. The gluon will cause the quark to change its colour from blue to red. That is, in symbolic terms. So you apply G R naught B, so that's a red and anti-blue gluon. You apply that to, or it interacts with a QB, that's a blue-coloured quark, and turns it into a red-coloured quark, a QR. So in other words, G R naught B acting on QB gives QR. Okay? If you want to see these equations, these interaction equations, as you could call them, have a look at the paper, the essay, the text essay. You can get the link from you can see it on my website under essays. In other words, the red anti-blue gluon acts on the blue-coloured charged quark and converts it into a red colour charged quark. Note that before the interaction there were three charges, a red, an anti-blue, both on the gluon, and a blue on the quark. During the interaction, the anti-blue of the gluon and the blue of the quark cancel, leaving only a red, which is now the colour charge of the outgoing quark. The colours are conserved, so as much red as before as after the interaction. That's what conserved means, meaning it doesn't change. What would happen if a red anti-blue gluon, so that would be a G R naught B, interacted with a red quark, QR? Question mark. Nothing. Such an interaction is forbidden in nature because the colour charges in this case are not conserved. That is, before the interaction we have a red and an anti-blue charge on the gluon and a red on the quark. If the quark absorbed the gluon and changed its colour from red to blue, then the final charge would be just blue. But that doesn't match the two reds and one anti-blue charges before the interaction. The colours are not conserved, so this interaction is QCD forbidden. This colour conservation operates with the emission of a gluon as well. For example, a red quark, QR, could emit a red anti-blue gluon, that is a GR naught B, and become a blue quark, QB. This emission can be represented as, so a red quark, QR, becomes or emits a gluon, red not blue, or R not B, converting the quark into a blue quark, so QB. So QR goes to QB plus GR not B. Okay? Again, have a look in the text if you want to see the actual equation. Note that the colours are conserved. The blue and anti-blue cancel each other, leaving a red on both sides. Colour conservation is one of the basic natural laws of QCD, quantum chromo. Chromo means colour, quantum chromodynamics. And QCD is all about the interactions involving the colour force. It's a type of charge, not electrical, ordinary electrical charge, but the strong force type charge. The same name, but anyway. Now, a gluon that is emitted by one quark and can be absorbed. Now, a gluon that is emitted by one quark can be absorbed by another quark, rather like the way a photon can be emitted and absorbed by two electrically charged particles, which is the basis of the study of quantum electrodynamics, QED. By emitting and absorbing gluons, two quarks can interact with each other and influence each other. I will make heavy use of this phenomenon, as will soon become clear. 5. The aha moment. Probably some of you have already had an aha moment on how you might implement a Femtotech-based computing, based only on what I have said above. Once I had read about the colour charges and gluon emission and absorption, I had my aha moment. I felt I had found a way to compute at the femtometer scale using quarks and gluons, at least in principle. For difficulties facing the practical engineering of these ideas, see towards the end of this essay. The aha moment gave me the following basic ideas. A. Represent a bit by the colour of a quark. Core idea. right? A red for 1 and a blue for 0. I didn't need to use green. B. To change the state, that is 1 to 0 or 0 to 1, change the colour of the quark from red to blue, or vice versa. C. To change the colour of a quark, use an appropriately emitted gluon, that is, one possessing the appropriate bi-colouring. D. To implement logic gates, and this was the creative challenging part, use a sequence of gluon emission and absorption of the same gluon. Critical idea. 6. Mapping the gates to quark-gluon interactions. Before I get into the specifics of the mappings, I need to introduce a fictional didactic device that I call a quark chamber. That is, a region of space, perhaps as small as a nucleon, for example a sphere, in which a quark enters at one end, interacts or fails to interact, and exits at the other end. Also entering or exiting the quark chamber is a gluon. In the case of gluon emission, the gluon exits the quark chamber. In the case of gluon absorption, the gluon enters the quark chamber and is absorbed within it. NOT gate. Fill the quark chamber with 2 gluons, that is a GR-NOT-B, so it's a gluon that's bicoloured, red and not B or anti-B, and a gluon B-not-R, so gluon blue, anti-red. If a red quark, QR, enters the quark chamber, it will not interact with the gluon red, not anti-blue, so GR-not-B, gluon, but will be converted to a blue quark by absorption of a G blue anti-red gluon, so a GB-not-R gluon, and will exit the quark chamber as a blue quark according to the interaction. So gluon blue anti-red, so GB-not-R, interacts with a red quark, so a QR, giving a blue quark. An ipso facto interaction will occur for a blue quark entering the quark chamber according to the interaction G red anti-blue acting on a blue quark, so QB, gives a red quark, QR. We thus have a NOT gate. A red quark is converted to a blue quark, 1 to 0, and a blue quark is converted to a red quark, 0 to 1. This is the definition of a NOT gate. OR gate. To implement an OR gate, it's a bit more complicated. We need 2 quark chambers, A and B. Chamber A is a gluon generating chamber. If a red quark enters chamber A red anti-blue gluon, GR-not-B, emission is caused in the chamber, and the gluon then exits. The resulting blue quark is ignored. If a blue quark enters chamber A, nothing happens. No gluon exits the chamber. We now have 4 cases to consider. A. Red 1, red 2. That is, a red quark 1 enters chamber A, and a second red quark 2 enters chamber B. Now you need to concentrate. In fact, it's probably essential that you look at the text version of this essay to follow this, because now it gets like heavy pure math, like lots of logic, and you need to concentrate. You really need to put on your thinking cap now. So concentrate, okay? The red quark QR1 entering chamber A generates a GR-not-B gluon that enters chamber B. This gluon has no effect on the red QR2 entering chamber B at the same time. The red QR2 then passes out of chamber B unaffected. In other words, the output quark from chamber B is red. Hence, if the inputs are red 1 and red 2, the output quark is red. B. Red 1, blue 2. The red quark QR1 entering chamber A generates GR-not-B gluon that enters chamber B. The blue quark QB2 that enters chamber B is converted to a red quark QR2. that then exits chamber B. In other words, the output quark from chamber B is red. Hence, if the inputs are red 1 and blue 2, the output quark is red. C. Blue 1, red 2. The blue quark, QB1, entering chamber A, generates no gluon, so no gluon enters chamber B. The red quark, QR2, that enters chamber B, then exits unchanged. In other words, the output quark from chamber B is red. Hence, if the inputs are blue 1 and red 2, the output quark is red. D. Blue 1, blue 2. The blue quark, QB1, entering chamber A, generates no gluon, so no gluon enters chamber B. The blue quark, QB2, that enters chamber B, then exits chamber B unchanged. In other words, the output quark from chamber B is blue. Hence, if the inputs are blue 1 and blue 2, the output quark is blue. Thus, the specifications of an OR gate are satisfied. AND gate. The AND gate is a bit more complicated still. It contains 3 chambers, A, B, C. Chambers A and B both output a red quark if the input is a red quark, and a blue anti-red gluon if G, B, not R, if the input is a blue quark. This time, instead of dealing with single events, think in terms of a stream of input and output quarks. Chamber C has as input the outputs of chambers A and B, as well as a fixed red quark, QR3 input, for reasons that will soon become clear. We again have 4 cases to consider. A. Red 1, red 2. That is, red quarks 1 enter chamber A, and red quarks 2 enter chamber B. The red quarks QR1 and QR2 pass unchanged into chamber C, along with the fixed red quarks QR3. There are only red quarks in chamber C, so only red quarks can exit chamber C. In other words, the output quarks from chamber C are red. Hence, if the inputs are red 1 and red 2, the output quarks are red. Now thinking in terms of streams of quarks. B. Red 1, blue 2. That is, red quarks 1 enter chamber A, and blue quarks 2 enter chamber B. The red quarks QR1 pass unchanged into chamber C, along with the fixed red quarks QR3. The blue quarks QB2 that enter chamber B generate blue anti-red gluons, that's GB not R, which pass into chamber C. These gluons convert all the red quarks in chamber C to blue gluons, so that only blue quarks exit from chamber C. Hence, if the inputs are red 1 and blue 2, the output quarks are blue. C. Blue 1, red 2. That is, blue quarks 1 enter chamber A, and red quarks 2 enter chamber B. The blue quarks, QB1, that enter chamber A generate blue anti-red gluons, that's GB not R, which pass into chamber C. The red quarks, QR2, that enter chamber B pass unchanged into chamber C, along with the fixed red quarks, QR3. These gluons convert all the red quarks in chamber C to blue gluons, so that only blue quarks exit from chamber C. Hence, if the inputs are blue 1 and red 2, the output quarks are blue. D. Blue 1, blue 2. That is, blue quarks 1 enter chamber A, and blue quarks 2 enter chamber B. The blue quarks QB1 and QB2 both generate blue anti-red gluons, GB not R, which pass into chamber C. These gluons convert the fixed red quarks entering chamber C to blue gluons, so that only blue quarks exit from the chamber C. Hence, if the inputs are blue 1 and blue 2, the output quarks are blue. Thus, the specifications of an AND gate are satisfied. Now that all 3 gates have been mapped to quark-gluon interactions in QCD, one has an in-principle recipe for femtometer scale computation. 7. Engineering challenges. However, the practical engineering problems remain, especially when considering something called asymptotic freedom, which says that quarks interact weakly when close together, but immensely strongly as they separate. rather like a tough rubber band being stretched. The more it's stretched, the greater the potential energy it has, similarly with the 3 quarks inside a nucleon. A nucleon is stable in the nucleus because it has 3 quarks. One is red, another blue, and the third green. These 3 colours sum to white, rather like a spinning colour wheel of equally sized red, blue and green sectors, which is analogous to the way an atom with its positively charged nucleus and its negatively charged electrons sum to neutrality. However, if one attempts to extract a quark from the nucleon, the gluons between the extracting quark and the other 2 quarks behave in complex nonlinear ways, interacting with other gluons to form a hugely powerful resistance until the potential energy is so great that a quark-antiquark pair can be formed, which combine to form a pion, pi meson. Mesons consist of 2 quarks, that is a quark and its antiquark. Hence, it seems impossible to isolate a quark or a gluon. Experimentally, no quark or gluon has ever been isolated. Experimentalists have virtually given up trying. Hence, the implicit assumption in the above models, namely that isolated quarks and gluons are used, seems unphysical and unrealistic. But if the gluons and quarks are close together, the stretching rubber band phenomenon does not occur. There may be particles that contain more than 3 quarks, the so-called exotics, which may have 3n quarks, that is a multiple of 3 to maintain colour neutrality, whiteness, by summing an equal number of red, blue and green coloured charges. There may also be glue balls that consist only of gluons that interact in highly nonlinear and hence complex ways. Another possibility is to heat up the quark/gluon complex so much that one obtains a quark-gluon plasma. At a critical temperature, after cooling the plasma, quark-gluon chains may start forming that may interact in ways similar to the way molecules interact within the cell, that is, by complementary lock and key touching. 8. Conclusions. The above femtometer scale computation models are in principle only. To make them practical will probably require new thinking to ensure that they are compatible with the severe constraints imposed by the principles of QCD, for example, quark confinement and asymptotic freedom. Asymptotic freedom, that's when quarks are so close to each other they effectively don't interact, they're just free to behave individually, independently of the presence of others. Hopefully this essay will stimulate other researchers to enter this new research field of Femtotech. Perhaps the other side of technology, that is the building stuff side, in contrast with the computational side, can be implemented with glue balls as well, or with quark/gluon condensates. Ad libbing now, a couple of years after I read this, I did find a way to use femtometer scale particles to build things with. Technically, the critical concept was the idea of using what I called pentaquark, so 5 quarks, pentaquark bracelets. I'll make a flyer, a video on that. So I now have femtometer scale computation and engineering, a means to build stuff. One thing is clear: if humanity does not make any progress along the lines of Femtotech, sooner or later human beings or our artificially intelligent successors will be scratching at the nanotech walls that confine us. One final comment. I'm thinking of trying to create an attotech, that is on the scale of 10 to the minus 18 of meters, by using the weak force particles, W and Z particles, that interact not only with quarks but with the much lighter leptons. For example, electrons